All right, welcome everyone to our September lecture series. Today we're going to be going through a revision session for chemistry units 3 and units 4. So hopefully you guys have finished your mocks by now and you're getting ready to sit those final external exams. So just a little bit about ATAR notes, specifically our lecture series. So we've been running lectures since about 2015, and roughly since about 2020, we've been running them entirely online, which is really great because then they're super accessible for everyone. And yeah, we can reach more people than we could before. So a couple of other things that we have got available. So if you head to our website, atarnotes.com, you can find pretty much everything here. We have our study notes, different videos. We've got all the lecture recordings. So if there's any lectures from this week that you aren't able to attend, you can always find the recording afterwards. And the same goes for this lecture as well. We have like online Q&A discussions. We've got newsletters, articles about pretty much everything to do with your last couple of years of high school, and lots of study tips as well. So definitely go and check out the website. Alrighty. So, like I said before, we're going to be going through chemistry units 3 and unit 4 revision. So this is separate to our Head Start lecture. So that's, I believe, happening possibly at the same time, but it'll happen sometime this week. That will be more for year 11 students who are now starting unit 3 for the first time. And my name is Boyana, haven't introduced myself yet, and I'll be taking you guys through today. So a couple of little things quickly is that you can watch the recording back after the session, so feel free to jump back onto this webpage and the recording will be where you can see the lecture at the moment. And the other thing as well is that we do have an active Q&A happening the entire lecture length. So any questions you have throughout, please ask questions in the Q&A section and we can respond to you as the lecture's going on. So yeah, definitely make the most of today, get some, really good revision out of it. So yeah, we're not going to be looking at a lot of content, like we're not going to just be looking at raw content. Today we'll be more focusing on practice questions. So with our exam practice questions, we'll cover a few different types. So we'll have multiple choice, some short answer. We're going to look at cognitive verbs and how to maximize your marks. So we're not going to be just going through questions, but I'll also actually take you through the process of how to approach exam style questions. And you can see at the bottom as well, we have our different topics. So we'll be looking at equilibrium, redox, organic chem, and chemical synthesis as kind of our main focus topics for today. So again, if there are other topics or more questions you want to kind of delve into, then there's lots of ATAR Notes resources that you can find related to pretty much everything that you might want to cover in chem. So again, make sure to ask lots of questions. A little bit of background about me. I'm in my last year of my science degree at UQ. And then next year I'll have a year off, and the year afterwards I start medicine at UQ as well. So that is my kind of academic background. I did year 12 at Brisbane State High School. And yeah, that's a little bit about me. So I'll be finishing my undergrad degree in about a month or so, which is very exciting. But yeah, ask lots of questions. I'll try and give my best advice as well as we go throughout about how to study for certain topics. But once again, any questions you've got, just chuck it down below. Okay, so we're going to start straight off with some equilibrium questions. So with our multiple choice questions, I want you guys to have a think about maybe even reflect on your mock exams. I know they can be quite rough for a lot of people, but I want you to have a think about what was your approach to multiple choice questions. So we want to think about how do we approach individual questions, and then also how do we approach the whole like paper one multiple choice section as a whole. So for example, for individual questions, you want to have a think about, are you using process of elimination effectively? Is there another way that you can kind of flag whether or not a question is worth even doing at that time, or do you want to save time, complete everything else, and come back to it? So that's just a couple of things to have a think about. But we'll go through this question. So it asks, which of the following correctly describes the action of a catalyst? So the first option is catalysts increase the activation energy of a reaction, but affect the position of equilibrium. We have catalysts decrease the activation energy of a reaction, but do not affect the position of equilibrium. We have no effect on activation energy and no effect on equilibrium position. or we can have a decrease in activation energy and then have an effect on the position of equilibrium. So from this question, we've got two main components to think about. We have to think about what do catalysts do for activation energy of a reaction and also for position of equilibrium. So the kind of process here is that we want to think about what do catalysts do. So catalysts kind of help chemical reactions happen more efficiently. And the way they do that is that they lower the amount of energy required for the actual reaction to take place. So that means that we're going to have a reduction in our activation energy. So I don't know if you've seen before, it probably will be quite familiar, but we can have these energy profile diagrams. And basically this is showing like the progress of the reaction, and then this is the amount of energy. That's kind of like time and energy there. So if we're thinking about, for example here, our reactants have a certain amount of energy, what that are. So our activation energy is a certain amount of energy that we need to overcome before we can complete the reaction and end up with the amount of energy we need for our products. So if I wanted to label this, this would be our activation energy. So EA there. So what a catalyst does is that all it does is the level of energy in the reactants and the product stays the same, but now instead what we have is there is less energy needed to kind of get over that activation energy and then finish the reaction. So if we want to sketch over the top of that, for example, with a catalyst, it might look something like that, where now our activation energy is much, much smaller with catalyst. Okay, that's my little sketch there. So that's what a catalyst does. So that means we're going to have a look at our options now and see what we can rule out. So we don't increase the activation energy, so we can rule out option A completely. So we have decrease the activation energy, so B is still potential answer. For C, so catalysts have no effect on the activation energy, so that's going to be incorrect as well. And then D is also another possibly correct answer. So now we're going to have to move on to position of equilibrium. So really important with catalysts and equilibrium is that they don't change. Like we kind of see with the energy here, reactants and products don't really change in their amount of energy. Same way, catalysts will not affect how much reactant or product there is at equilibrium. So if you want a really kind of easy way to remember it, catalysts help you get to equilibrium faster, but they do not actually change the equilibrium position. So they don't change the amount of reactants or products at your equilibrium. So that means we're going to have no effect on the position of equilibrium. So that means now we can go and rule out D because it's saying it does have an effect. And therefore, the correct answer is going to be B. So that's a little process of elimination. And if you want to really try and maximize your time in the external, have a think about, if you can immediately just see that there's something wrong with the answer. So for example, we just started with looking at activation energy, then you can already could rule out 2 out of 4 of the options just by looking at one part of the actual answer. And then we can use the last little bit to finally get the correct one. Yeah, so that's a little bit about the multiple choice process, and that's our correct answer B. Okay. So the next question, for the following reaction, which reaction direction will be favored if the temperature of the reaction is decreased? All right, so I also invite you guys to have a go at these questions. If you want, you can actually pause. If you're watching the recording back, you can pause the recording. I'll give you maybe a minute or so to have a think about the question, and then we'll go through it together. So think about the key parts of what the question is actually asking, and then again, see if you can maybe use a little bit of process of elimination in those, in trying to figure out the correct answer option. So while you're having a go, I'm just going to kind of break down the question a little bit. Okay, so hopefully you've had a little bit of a go at considering this question. So first thing I would have a look at is the actual wording of the question itself. So we're looking at which reaction direction will be favored. So we want to think about forward or reverse, or any combination of that. And which direction will be favored if the temperature of the reaction is decreased. So here we're looking at the topic of factors that affect equilibrium. So if you want to think about the actual equation that we've been given, we want to try and figure out what's happening with our temperature here. So it's really important that they have given us the delta H value, because that's going to give us important information about what kind of reaction we have. So because this value is positive, that means we have got an endothermic reaction. And endothermic reaction means that we're going to be absorbing heat to get to our products. Absorbing heat to create those products. Okay, so then that means that if we're looking at our equation, a really useful tip I have for these kinds of questions with temperature is to actually write in heat as if it's a product, like as if it's an actual chemical species, like if it's a reactant or product. So what that means is we're going to be absorbing heat in this reaction. I'm going to put heat at the front there. And then we can kind of treat a temperature increase or decrease in the same way we kind of treat these questions related to concentration. So what I mean by that is if we want to increase heat, we go shift to the side that has heat on it. If we want to decrease heat, shift away from that side. So if we've decreased the temperature of the reaction, Le Chatelier's principle means that the reaction is going to try and increase. It's going to try and increase to get back close to equilibrium. So that means they're going to be favoring the reaction that has heat as a product. So that means going to be shifting that way. So in that way, we can say we're going to be favoring the reverse reaction. All right, I'll have a look at the next one. So for the following reaction, which reaction direction will be favored if the concentration of NO2 is decreased? So same equation, I'm pretty sure. Same equation, different change to the system. So again, I'll give you a little bit of time, have a go at it, and then we'll go through the answer together. All right, so I'll start going through it. So if concentration of NO2 is decreased, I think we've gone down here, the system's going to shift in a way that's going to try and replenish the decrease in concentration of the NO2. So that means we're going to be shifting to the right to replace that lost NO2. So if we're shifting that way, that means we're going to be favoring the forward reaction. And we can say that A is our correct answer. All right, so that was a little bit looking at how to actually predict which way are we going to shift. Now we have a different kind of question looking at factors that affect equilibrium. So for the following reaction, the following graph can be plotted. So what stress has occurred in the system? Label the graph with what is happening at each stage. So we can kind of see that we have a stress occurring some point after equilibrium has been established the first time. So just to revise, equilibrium is when we have equal rates of forward and reverse reaction. So they're going to be producing, it doesn't matter how much there is on each side of the equation, but they're going to be producing each side at the same time, so then concentration stays constant. So really important for this question. And just in general with graphs and exams, always have a look at the x and y axis, because you never know what they could have put. You might confuse this one for a graph where we have time and concentration rather than time and rate of reaction. So yeah, have a consideration of this little graph here. And again, any questions, please pop them into the Q&A, get you an answer. The questions can be asked anonymously, so don't worry about anything there. But yeah, have a go at this one, trying to kind of consider what our stress is. All right, I think we'll have a look at the answer now. Okay, cool. I'll draw it onto here. So if we have a rate being disrupted here, so this is where we've achieved equilibrium the first time. And then we have a sudden increase in the forward reaction. So that means that all of a sudden we've had a very sudden spike in the reaction rate there. So what this is suggestive of, because our reverse reaction is kind of just following and catching up to the forward reaction. So here we can kind of consider, well, what would make the forward reaction kind of just spontaneously occur a lot faster? And that's most likely going to happen from an actual change in concentration. So these rate graphs are a little bit more difficult than the typical concentration graphs, and I wouldn't say that they're very common. But for here, we can say that we have stress. We can either have a few options, actually. We've added AB. So we've actually increased the concentration. It's going to increase the rate of the forward reaction. We can also say that we've had a change in pressure. So that's looking at the fact that we have 3 moles of product and 2 moles of reactant. So to favor the forward reaction, that means that we'd have to favor the side that's going to be producing more moles. So that means we've decreased the pressure, and the system's going to try and increase pressure by making more moles, just making the right-hand side. So that means we have decreased pressure. That could also cause an increase in the forward rate of reaction, and then reverse will just increase to kind of match it. Yeah. Any questions again, please drop it into the chat. So our next one's also another graph question. Now we have a concentration time question, so that's a more common one. This one's looking at after how many seconds does the system reach equilibrium? So again, have a go at this question. There, as a hint, there are quite a few different intervals that have where equilibrium is reached. So what I might actually write is, might do instead in which time intervals. So have a go at that for the next 30 seconds or so, and then we'll go through it together. Okay. So if we're having a think about this system, so we want to think about, so equilibrium, what does it look like in terms of concentration? So the answer there is equilibrium is achieved when the concentration of all of our reactants and products remains constant. So a common kind of misconception that can occur is that the concentration needs to be equal. Definitely not the case. Rate of reaction needs to be equal, as we saw in the last graph, but for concentration, it just needs to stay at what it is. So we'll say here, concentration of reactants and products constant. So I'm just going to highlight what intervals those actually end up being. So if we're looking here, our first kind of bit, I'd say it's probably from about 10 to 20 seconds. So we can put that as our first one. Our next one is, so the next kind of, then we have a little change there in the system. We have another stretch there. So that's from about, I don't know, maybe say like 21 or 22 seconds, roughly. Let's say 22 seconds, all the way up until looks like it's 35. So this one stops being constant at 35, even though this one's, I'd say, slightly afterwards. So I'd say 35 seconds. And then our last one is from here to here. So again, we have to be quite careful about when do we actually have everything staying constant. So, sorry, I don't know if you can hear that, Carl. So the hydrogen and the iodine, those are constant from 40. Even though the HI is constant from a little bit earlier, we'll go from 40 because that's when they both are. And it goes until the end of the graph, so that's 50 seconds. So that's a good little revision on what equilibrium looks like on a concentration time graph. Now here we have a different type of question, same system though. So calculate the value of the equilibrium constant, and we're going to go for, what was I going to say? No, actually, yeah, just have a go calculating the equilibrium constant. We'll go through working out together in 2 seconds. And also just for consistency, I'll be using the values from this equilibrium section there. Also, if anyone's got any general questions about external prep or yeah, absolutely anything related to the Chem External, you know, based on our experiences or I don't know, your own kind of questions based on how you went with your mock exams or how you've been going to chemistry in general this year, again, please feel free to ask. No question is a silly question. So anything we can help with, please make the most of the couple hours we got today. All right, I'm going to start writing out the equilibrium constant. So first we'll start off with writing just the equilibrium expression. So for our equilibrium here, I'm going to think of this as we basically have our products over our reactant. So specifically our products here, so we have the HI gas. So we'll put the concentration of that. And it's to the power of 2 because of the coefficient here. And for reactants on the bottom, we have our H2 gas and our I2 gas. And neither of those have any powers because they don't have any coefficients. They've only got 1 in the front. So now that we've got that, we can then sub in our values for concentration from that section of the graph. So for HI, which is this line here, we have a value of 6. We put 6 squared over, and then both of these are at, I'd say, 0.75. So that's 0.75 times 0.75. And then, so I'm just going to move that so you can see it. And if we're going to just pop that in our calculator, so I'm just going to chuck it in the graphics calculator. Also, good practice is just to use, when you're doing practice questions, use the calculator that you'll use on the actual day, whether that be your scientific calculator or graphics calculator or whatever you've got. So if we put those values in, we should end up with an answer of 64. So that means that we've got a massive favoring of the product at equilibrium. As you can probably see from the graph, we've got a lot of products compared to our reactants. So it makes sense why it's so much greater than 1, because keep in mind this is a little ratio here. So depending on if it's less than 1, greater than 1, and by how much, we can kind of interpret a little bit about what the reactants and products are like at equilibrium. Sweet. Okay, next question. So explain what happened at t equals 20 seconds. So we're going to look at this time point here. Have a think about what's happened. So what I'm going to say here is that we have a very sudden drop in the products in the HI, and we have what kind of looks like just a really gradual reaction in the H2I2. So here we have a spike, which is something to definitely look out for. Whereas in our reactants, what we have is just this little kind of kind of like a reaction to the stress rather than the stress itself. So it seems like we've done something to the HI. So because we have a spike in that HI going down, that's suggestive that we've just decreased the concentration quite suddenly, because you can see concentration is just dropping immediately. If we had a spike in our reactants as well, and if we had a sudden change in concentration, because C equals N over V, that would be suggestive of a change in pressure or volume, where we've just changed volume for everything, so that's going to change concentration for everything. But because we only have that sudden change in the HI, that means that we have got a decrease in concentration. So we've decreased the concentration of HI. And what that means is that the H2 and the I2 is just kind of reacting accordingly by therefore decreasing their concentration, because we're favoring the forward reaction at that point. Yeah, so that's really good practice. A good practice question to do is just practicing how to identify different types of stresses based on the features of the graph. Alrighty, so if the change at t equals 35 seconds is due to an increase in temperature, is the reaction exothermic or endothermic? So we're looking at this change over here. So again, think about which way has our reaction shifted, and then what does that mean? You can kind of use the trick I mentioned before, like have a think about what does that mean for actual, where is heat sitting? So let's have a look at actually what's happening. So we've got a decrease in HI, and we have an increase in our reactants, so in the H2 and the I2. So if we've increased reactants, decreased products, that means we're shifting to the left. Which is favoring our reverse reaction. Okay, so if we favored our reverse reaction, and what's happened is an increase in temperature. So we increase temperature, so what the system will want to do is to bring it back down, bring the temperature back down. So decrease temp. So that means favoring the reverse reaction is somehow decreasing the temperature of the whole system. So if we're decreasing temperature, that means we're using up heat. So that means when we shift to the left here, we're using up heat. So that means heat is sitting on the right-hand side, as like that product that I was kind of mentioning before. So if we've done that, then we can kind of infer from there that the system, so just looking at it baseline, like left to right that way, that is us having an exothermic reaction where the products are releasing heat. So therefore, we can say the reaction is exothermic. So again, this is all recorded. So if there's any explanation that you want to kind of just go over again, any questions, you can also download these slides with all the answers on them. Please have a look at the recording again and work through any concepts. And if you've got any questions now, drop them into the Q&A. All right, so here we have a pH question. So calculate the pH of the solution that results when 40 mils of 0.1 molar NH3 is diluted with 20 mils of distilled water. And we have a Kb value there. So this is a multiple choice question, but it does involve some calculations. So have a go at that one briefly, and then we'll go through the working out together. Okay, so I'm going to go on to the answer now. So we can identify the information we've got. So we know how much we have, what concentration of NH3 initially, and then we have how much we have diluted it with. We've also got our Kb value, and I'm going to try and use that to figure out what is our pH ultimately. So you can see we have quite a few, different little steps and equations here. So the first one is that we want to think about our actual concentration in our volume. So this equation here, you might have seen also, this is the same as just C1V1 equals C2V2. So we sub in our C1V1 for the original 40 mils, and then we also put in our new, so once we've added 20 mils, that's why we have 60 mils here, and we have an unknown concentration. So rearranging that equation, we get our concentration is 0.0667. And then we have our Kb expression. So we have the Kb value, we can sub that in, and this is our Kb equation based off of here. So in our Kb equation, we just want to think, that's just purely just the dissociation of the base in some water. So once we've actually written that out, and we turn it into the expression, so we have NH4 and OH minus on the top and NH3 on the bottom. So what this next line is incorporating an ice table. So again, let's have our equation. So there should be a little plus there. So if we've started off with a certain amount, certain concentration of our NH3, which was 0.0667. Water we just ignore because it's a liquid, and we had none of this to start off with. So once we dissociate that NH3, the changes that we have minus x here, plus x, and plus x. So then at equilibrium, we have 0.0667 minus x, and x, and x. So that's what we've subbed into the Kb expression. Now we can ignore the x in 0.0667 because it's a very weak, we can just recognize ammonia as a weak base. So then the kind of change is so small that we don't even really need to factor it in. But again, if you left it in, I don't think it would affect the answer too much. So then we get what our x value is, and that's going to be equal to our OH minus. So if we take the negative log of our OH minus concentration, that gives us our 2.964 as our pOH of the solution. Now we want to find the pH, so to get that, we just go 14 minus our pOH, and that's how we get our answer of 11.036. All right, cool. So quite a few different steps in there. Again, any questions, please do ask. Then here we have a example of a actual titration question. So this is a really good baseline titration equation, or a question that uses the kind of baseline titration equation to figure out an unknown concentration. So good practice question. Please have a go. But actually, just in the interest of time, I might just take us through the question immediately. So we have 38 mils of 0.75 molar sodium hydroxide solution, and that will completely neutralize 155 mils of a sulfuric acid solution. So what's the concentration of the sulfuric acid solution? So first thing with these questions is to always write out our equation. So here we have the sodium hydroxide and our sulfuric acid neutralizing each other to form Na2SO4 and also water as well. So then important that we have a balanced equation as well, because we have 2 hydrogens, which means that we're going to need 2 base kind of molecules for every hydrogen. So the next thing we can kind of just calculate from there. The main equation that we're using is C equals N over V. So for one side of the equation, we can have the rearrangement to make it look like this. We have CV over N will equal CV over N of the acid and the base, because to neutralize, we have equal moles of acid and base. So that's how we can kind of put those things together, because the number of moles there are equal. So then we can sub in the values that we have from the question to solve for our unknown concentration of A. So that means we end up with just concentration equals C the base, V of the base, N of the base, over N, oh no, that'd be N of the acid, my bad, N of the base, multiplied by the, what else do we have there? Concentration of the acid. Oh, not the concentration, sorry, the volume of the acid, goodness me. So if we sub all those values in, we end up with 0.092 molar of sulfuric acid. So basically the steps here are that we want to find, so out of C equals N over V for the base, we have our volume and also our concentration. So we rearrange to solve for N of the base. Number of moles of base equals number of moles of acid at neutralization of the titration. So that N value is the same for the acid. So again, we want to find our concentration of the acid, so we sub in that N value from the base, and the volume we have is the 155 mils. So then that's how we find our missing concentration. So there's a couple of different ways you can kind of approach that question, but that's probably just the main gist of it there. Okay, so now I'm going to start looking at some redox questions. Again, anything related to equilibrium, acids, bases, any questions there, please put it into the chat, and we'll be able to respond there, have a bit of a conversation about anything you're stuck on. We're going to have a look at some redox questions now. So have a go at balancing the following reaction under acidic conditions, and then I'll take you guys through the answers shortly. Have a go at least with the first couple of steps, and then we can step through it together. So the first thing we want to start off with is making sure that we assign our oxidation numbers correctly, because we want to focus on getting the right half equations to start the balancing process. So we'll start off with actually having a look at that first. And I'll actually go back on here and I'll write it on top. So for our Cr2O72-, the first thing we would assign here is our oxygen. So we would actually assign that a -2. Now we have 7 oxygens, so that gives us a -14 all up from oxygen. And we want to get it all the way up to -2. So we have 2 of our Crs. So if we want to get that up to -2, we need to add 12 positive. And because we have 2 of these molecules, that means each one is a +6. So hopefully that process makes sense there. And then for our iron, it's just a standalone iron atom there. So that will just be +2, the charge of the actual iron. And same for the other 2 species as well. +3 and +3. So you can see here that our Cr has gone down from +6 to +3. So that means it's reduced. So my trick is, or what I kind of just used to remember, is a decrease in, so a reduction in oxidation number is reduce, you have a reduction reaction there. And then for our increase in oxidation, it's like more of an oxidation number, so you're going to be oxidizing. So that's what's happening with our iron there. It's going from +2 to +3. So an increase in oxidation number means that it is oxidizing. So that means if we had to write out our full reduction half equation there, it would be Cr2O72- giving you Cr3 plus. Then our one for oxidation would be Fe2 plus, giving you Fe3 plus. So over here, what we do is we have the full balanced half reaction there for both of them. But what we'll do first is actually, I'll step you guys through the balancing process for each individual half equation. So for the one on the left, we have to balance our non-oxygen, non-hydrogen elements first. So that's our Cr. So we have two on the, let's get a different color as well. We have two on the left and we have one on the right. So that means we're going to have to add a 2 at the front there. And then the other, the next step we have is we want to balance our oxygens. So if we have 7 oxygens on the left and none on the right, we're going to balance the oxygens by adding 7 waters onto the right-hand side. So that's always the next step after non-O or H elements, we always balance oxygen. And now we're going to balance hydrogen. So now, after we've added water, we have 14 hydrogens on the right and none on the left. So we're going to add 14 H plus onto the left-hand side. Now, our last step is to balance our charges. So we're going to add up the charges on the reactants and the product side and then add electrons to kind of balance it out wherever we need. So for our left-hand side, we have 14 H plus and then one molecule that's 2 minus. So that gives us a total of plus 12 on this side. Then on the right-hand side, we have a 3 plus ion and we have 2 of them. So that means our total charge, and then water is neutral, so total charge is plus 6. So therefore, to balance this out, we need to add electrons to the side that's more positive. So the more positive side is reactants. We're going to add electrons there, and we're going to add 6 of them to bring that plus 12 down to plus 6, because each electron has a minus 1 charge on it. That means our kind of next line there, we're going to add our 6 electrons, and then that gives us our 2Cr3 plus and 7H2O. Now that's our fully balanced half equation there for the reduction side. And then for the oxidizing side, so we have Fe2 plus and Fe3 plus. So let's go through the list. So non-oxygen, hydrogen elements are all balanced. Oxygen is not on either side, so it doesn't need balancing. Hydrogen isn't either. So all we have to do is the charges. So if charges are plus 2 and plus 3, I'm going to be adding 1 electron to the right-hand side to make them both plus 2. So that means we have Fe2 plus, giving you Fe3 plus, and 1 electron. So that's our kind of process there for working through the half reaction balancing step first. And a good way to check that you've done the right thing is checking where your electrons are. So for the reduction is gain of electrons, so they should be on the left-hand side, which is what we've got. And for oxidizing, or the oxidation half reaction, I should say, actually, we have 1 electron being lost on the right-hand side, which is good. So that's a good way to kind of just check your work as you're going through. Okay, so once we've balanced the half reactions, we need to combine them back again. So that was honestly probably most of the bulk. That's the bulk of the work for acidic condition balancing. So then we equalize electrons. So that means that we have to multiply one of these half reactions by some kind of coefficient in order to get a complete, we need to be able to cancel out the electrons so then we can get a complete equation. So if our so our reduction reaction had 6 electrons and our oxidation half reaction had 1 electron. That means if we multiply our bottom one by 6, that will give us, so like I said, multiply by a factor of 6, that will give us 6 electrons on the right-hand side, which means that when we add up all of our reactants and products together into one big equation, the electrons will cancel out, which is always what we want. So in this question, the only thing that ends up canceling out when we combine are the 6 electrons. So our final answer for the balanced equation is this one here. All right, awesome. A good balancing question. So we have another one here. Again, we'll start off with the actual balancing of the, what do you call it? No, sorry, we'll assign our oxidation numbers first, and then we'll balance our half equations and combine them again to make our final full one. So I'm going to step through the working out on the screen as we go and kind of just explain it bit by bit. But again, please, if you want, have a go at the same time, be a couple steps ahead of me, see if we're getting the same thing as we go along. That's a good way to practice. So we'll start with our oxidation, with our oxidation states, or oxidation numbers. So our Fe. Now that's, so our iron is just sitting there by itself and doesn't have a charge. So we assign it a 0. Then for our HCl, so we can think of this, might actually get up a periodic table. Again, another tip for practicing for externals is having the actual data book printed out and at your desk or wherever you are when you're doing practice questions, so then you can get used to using the data booklet that you'll have on the day. But for our HCl, we can assign our hydrogen a +1, and then our chlorine is going to be a -1. So it's good as well because they relate to their position in the periodic table. So chlorine is a -1 ion as well. And then hydrogen is our +1 as just a general rule. The only time when hydrogen is not a +1 is when it's in a peroxide. So that's our reactants done. And then for our products, we're going to start off with our H. We can assign that again +1 because it's not a peroxide. And then Cl4, we can make that a -1 from where it lies on the periodic table. And then iron, because it's a transition metal, we'll leave that one last. So we've got a +1 and then basically a -4 because we have 4 chlorines. So then we're going to get it up to neutral. That means we're going to make iron +3. And then H2 is sitting by itself. It's just going to be a 0 because we don't have a charge and we just have hydrogen there. So then now we're going to figure out which one's oxidizing, which one is reducing. So for our iron, that's going from 0 to +3. So that's an increase in oxidation number. So that's going to be oxidizing. And then for reducing, our hydrogen is actually going from +1 to 0, left to right. So then that's our other side. Okay, cool. So that's our half equations, and now we're going to go and balance those. So let's write them out. So reduction, HCl, H2, oxidation, 2H, Cl4. Alrighty, we'll start with our reduction half equation. So let's balance we're actually already balanced it as below. Okay, yes, sorry. So we'll actually go onto this slide because we have a bit of a different situation here because of how our hydrogen has worked out. So our half reactions that are already balanced are actually below. So the iron we just consider in terms of the, the ion itself. So like, I know they sound so similar, but like ion. So here our half equation, instead of considering, instead of considering Fe to Fe, HFeCl4, because we have, as you probably could have seen there, so if we're going to try and balance HCl and H2, we don't have Cl on both sides. Then that means we're going to just work with the ions. So we have Fe turning into Fe3+ and 3E-, and then for our hydrogens, we had the H+ and the HCl turning into H2 on the right-hand side. So we balance those out with our electrons, and then we can kind of incorporate them into our final answer. So we have 2 ions and 6H+ once we've multiplied them both to get, So this one multiplied by 2, multiplied by 3, so then we get 6e minus on both. So once that's done, then we can combine them into our final answer and write the ions back in their complete full thing. So we can write the H plus again in terms of HCl and the Fe 3 plus in terms of the actual full HFeCl4. So that's a bit of a different process because we have kind of unique molecules in that way. So if you ever get to a point, and that's actually kind of good, I just kind of went under the assumption that it was the same as the last one. If you ever get to a point where you get stuck, where you're thinking, I can't balance this because we have Cl here but no Cl there to balance, then that's why we just treat it as the H plus by itself, and then the H2. We balance that. And then when we finally write the answer with our combined half equations, that's when we can rewrite the ions in terms of their full molecules. All right, cool. We have another balancing question here as well. I just do a check of something. And okay, cool. So we've got 2 more redox questions. So we'll go through those, and then we'll have a brief 5-minute break or so. Let you go to the bathroom, ask any questions, and we can answer them before we go into the Unit 4 revision. So again, we have another balancing equation, balancing redox question. This is a really good skill to have as well because we're going to look at, we're looking at oxidation numbers, we're looking at what redox is by definition, how to identify redox reactions, and then obviously the balancing itself. So these are good questions in terms of revising a couple of different concepts at the same time. So let's start with our oxidation states. So oxygen, we start off with the -2 automatically, then to bring it up to -1. So this is all -6. I'm going to add 5. Then we have H2O2, so our oxygen is our -1, and then hydrogen is, -2, then hydrogen is our +2. So that's our peroxide there, where we have hydrogen and oxygen both in there. And then we have NO and O2, so 0, -2, +2. So if we jump to our half equations, so I might just have a little check of something briefly. Yes, okay, had to double check that. So in our peroxide, hydrogen becomes a +1 rather, oh sorry, not a +1, a -1, just double check our, okay, cool. So oxygen, we have, so this is a case where usually hydrogen is +1, whereas in a peroxide it becomes a -1, and then oxygen becomes our +1 instead. But I really do want to check that. Apologies, guys. No, okay, that's all good. So what we had before, so hydrogen stays as our +1, and oxygen, sorry, got the oxygen and the hydrogen confused. So the oxygen is what we have instead of it usually being its standard -2 because it's in a peroxide, where we have 1 hydrogen, every oxygen, then that means that we have our -1 instead to balance it out. So we start with hydrogen always being the +1 in this instance, and then oxygen, instead of being -2, is -1. So apologies for the confusion there, and also I think I might have mentioned that incorrectly earlier as well. But we'll put it in the chat as well, just to make that very, very clear. But yes, we'll go have a look now at the half reactions and how they balance out. So the half reactions, when they've already been balanced, are below. So we had the hydrogen. So we have the NO3, I'll just highlight it for us, NO3 minus, reducing into the NO. So like we saw before, it went from +5 to +2 for the nitrogen. And then for our oxidation half equation, we have our H2O2, and then forming our O2. So like we saw there before, oxygen went from -2 to our, oh not -2, sorry, from -1 to 0. So this oxygen to this oxygen. So then we follow the same half equation process of balancing hydrogen and oxygen, then balancing our charges with electrons. And then because we have 3 electrons on the top and 2 on the bottom, multiply the top equation by 2, multiply the bottom one by 3, and we end up with 6 electrons. And we can also cancel out some H plus, because we're going to have excess H plus on the left versus the right hand side. So once we've combined, the equation looks like that. And then we can also combine the hydrogen ion and the nitrate ion. I wouldn't be too fussed about that though in terms of an exam, but that's if we wanted to write that as an actual molecular equation where we don't have ions just floating around. They would usually bind together. And then just in the interest of time, so if you want to, actually I think it's a very similar question, but we have an extra balancing acidic conditions question there. Please have a look at that if you'd like to do some more practice. You can download the slides and then the solutions are all there as well. But following the same process that we had before. And now for our last redox question, I believe. Yeah, for our last redox question, so we're having a look at 2 half reactions of an electrochemical cell. So we're going to construct the redox reaction equation from the 2 half reactions and calculate the cell potential from the standard potentials and predict if the reaction is a reactant or product favored. So we're going to actually look at the thinking behind this question. So if we look at the half reactions and we want to combine the 2 together, so we can see here that our first one is gaining electrons. So that's our reduction. And the one on the bottom there is our oxidation because we're losing electrons. So then we can calculate our E cell value accordingly. So redox reaction equation, we combine them all out and we're just balancing them by making sure we balance out our electrons. So we'll multiply the top equation by 2, multiply the bottom equation by 5, and then combine them. So in a way, they've already given us those balanced half reactions. Once we combine that, we can calculate our E cell value. So we want to add the 2 E naught values together. So they're already written in the correct direction, reduction and oxidation. So we don't need to do any negative signs or anything crazy. We just need to add these 2 values to get 1.66 volts. Once we've added those 2 together, that means we have the product being favored. So what that means is that our reaction will happen spontaneously from left to right. If we had a negative value, then it would happen spontaneously from right to left and favor the reactants instead. So that's kind of how to interpret that question there. Alrighty, so we're about halfway through the questions and the topics, and also I think halfway through the lecture time as well. So I'll give a couple minutes of break, use this time, head to the bathroom, grab a snack before we do the second half of today. Also have a go at this question or any of the other questions if you want ahead of time. You can download the slides so you can actually, have a go at anything you want at the moment. But also ask any questions we can answer in the chat just about Unit 3, maybe, and then we'll proceed on to doing Unit 4. So I'm just going to go and grab a drink of water, and then we'll be back to continue. Alrighty, we will go through our next lot of content. So we'll be focusing on Unit 4 now. We'll be having a look at organic chem and then the second topic of chemical synthesis. So a little variety of questions again, but let's have a look at this first one. So just starting with looking at different organic compounds and naming them. So we want to name the hydrocarbon pictured below. So we can first have a think about, do we have any functional groups here? So we can kind of see it's just a straight carbon chain with nothing crazy happening. We don't have any double or triple bonds, and we don't have anything branching off the sides. So we can kind of then classify this as an alkane. So looking at the answer options, we can already rule out octine and octene because we don't have an alkyne with triple bond in it, and we don't have an octene with a double carbon bond either. So now the only difference between octane and nonane is how many carbons are in that chain. So here we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 means we're going to have the prefix oct, and that's going to be octane. So that's how A is our correct answer there. So yeah, we have octane. Now this next one here, so we want to write the name for the hydrocarbon pictured below. So now we can see we've got a bit more of a complicated one. We don't have any double or triple bonds or special functional groups yet, but we do have a lot of branching. So the way that this will kind of work to start off with is we want to think about figuring out what's our longest chain of carbons that we can make, because that's going to be our parent chain. So let's have a bit of a trial of some different ones. So if we start down here, go 1, 2, 3, 4, 5, 6, 7. I think that's going to be our longest one because this one down here, 1, 2, 3, 4, 5, 6 is only 6. So that way, our longest chain is from there to there. And then we also want to give our chain the numbering that's going to give our branches. So that means we have a branch here, here, and here. Oh, not there. And here are the lowest numbers. So if we number from the left, that means we're going to be going 1 off from the bottom. So 1, 2, 3, 4, 5, 6, 7. And then if we went the other way, it would be 1, 2, 3, 4. So we wouldn't actually start naming a branch until 4. Whereas if we go the other way, it'll be from 2. So we're going to number them the way that I've done in blue there. So just ignore that 3. So now that we've done that, let's start with actually just naming our parent chain. So we had 7 carbons, so that's going to be heptane. And that means we can then rule out B because we don't have hexane and we don't have pentane, so we can rule out D as well. Now we want to just think about naming our branches. So we have on 2, we have a methyl group because it's just 1 carbon. And then on 3, we also have a methyl group because that's 2 carbons. So then we can say we have 2,3-dimethyl. So important to put the di to indicate that we have 2 of the methyl branches. And then we have on the 4th carbon, we have an ethyl group because we have 2 carbons in this branch. So that's 4-ethyl. And we put ethyl at the front because we want to keep it in alphabetical order. So that's super, super messy, but hopefully you can just tell that's 4-ethyl 2,3-dimethyl heptane. So that's going to give us the correct answer of C. Alrighty, so then here we want to identify the functional group of the molecule pictured below. So the functional group, if we want to just circle it, is this segment here. Now this isn't a ketone because we have both a double bonded oxygen and an OH. It's not an aldehyde either because we have that OH. Ketones and aldehydes only have this segment in them. And then is it an ester? So an ester is where we would, instead of this H, have a continuation of the parent chain, which is not the case here. So not an ester. So therefore we can say this is a carboxylic acid functional group. So the answer is D for that one. Now here we want to identify the functional group of the molecule. Now our functional group is this hydroxyl group here. That's what's our kind of special thing about this molecule. And then we want to think about the actual, is it a primary or a secondary? So we can kind of exclude that. And then we want to think about, is this primary? And this is technically a hydroxyl group, so we can maybe not cross out that option just yet. But let's figure out if it's primary or secondary. So to figure out if it's primary or secondary, we want to look at the carbon the OH is actually attached to, and how many carbons are attached to that carbon. So we have 1 carbon and then 2 carbons directly off the one that the OH is attached to. So because it's 2, that means we have a secondary alcohol. And that's why our answer there is C. So something to keep in mind with the primary alcohols, because I get this question quite a bit, is that, so if we had OH, C, and then just hydrogens, versus C, C, then OH. So this one, you can kind of think of it, this is like a classic, I don't know, my pen did that. The one on the right is our classic kind of primary alcohol, because we have, so we have 1 carbon coming off of the carbon the OH is attached to, whereas the one on the left, it's still also a primary alcohol. It's just a special case because it's technically got nothing attached to that carbon, but we still classify it as primary. So just wanted to clear that up while we're here. Okay, so this question now is a bit more involved. We're looking at the physical properties and trends of organic compounds. So we're going to rank the molecules pictured below according to their boiling or melting points. So we're going to go from highest boiling melting point down to the lowest. So I'm going to do the left one, middle one, right one, and in which order. So have a little think, spend a minute, just think about the different characteristics of molecules that will alter your boiling or melting point, and then we're going to kind of use that to springboard our answer. So even though this is a multiple choice question, a really, well, I can't really say really popular because the externals have only been around for a few years, but a question that has come up before in the external exam is just looking at a short answer version of this type of question where you'll be presented with different molecules and you have to justify why they would have certain relative melting or boiling points. And the other one is also solubility to consider too. So we'll go through the answer in a second. Alrighty, so we're going to go from the right to the middle to the left. So that means this one here has our highest melting point / boiling point. This is our middle, kind of medium melting point, boiling point relative to the other two. And the one on the left is our lowest melting point / boiling point. So let's have a think about why that is. So what are the actual things that affect I'm just going to say melting point, but it's the same thing for boiling point. So if we're affecting our melting point, we want to think about what is the level of intermolecular force keeping these molecules together, and that's going to come from our functional groups. So first thing is looking at functional groups. Another thing we can look at is our size of the molecule. So a bigger molecule will have more dispersion forces, which will keep the molecules more kind of tightly knit, which means it'll be harder to separate them in order to change states. So that's another thing to consider. And then the third factor is also branching. Now that's not really an issue for this question because we have all kind of the same, there's no special branching in any of these. They're all just kind of straight chain with a functional group, but that's another thing to consider. So the more branched molecules are, the less close they can stack, the less effective their dispersion forces are, therefore the lower their melting point. Alrighty, so here the highest melting point has the strongest intermolecular force because we have our dipole here and we have our hydrogen bonding here. So we have H bonding compared to this molecule. So this ketone here doesn't have H bonding, but it does have dipole. So that's the next strongest. And then our alkane over here has the lowest melting point because It just has your, what do you call it? Dispersion forces. So we'll write that down too. Now, another thing to just kind of take note of is the length of these molecules. So we have 1, 2, 3, 4, 5, 6, 7, 8 carbons there. 1, 2, 3, 4, 5, 6, 7, 8. Okay, never mind. These all have 8 carbons. So we can't consider size, and none of them have any special branches. So the differentiating factor here is the actual functional groups present on the molecules. All right, now the same molecules, but we're going to rank them according to their solubility now. We're going to go from highest solubility to lowest solubility. So again, consider the factors we were discussing before, but for solubility, if you want to be soluble in organic solvents, that means so these bad boys are polar. And if we're looking at solubility of these other molecules, the kind of phrase I like to stick with is like dissolves like. So that means to dissolve in something polar, you also have to be polar. Oh, sorry, this is non-polar. Water is polar, before I confuse you guys. So organic solvents, think like things like fat, non-polar. But if you want something to dissolve in something that's non-polar, you have to put something non-polar in it. If you want to be soluble in water, which is polar, you also have to be polar. So that's the idea here. So if we look at the actual order, it's going to be left, middle, right. So we're going back this way now. So this is the most soluble. So this one, so our alkane is the most soluble in organic solvents because it's the most non-polar. We don't have any polar bonds. This is the non-polar molecule, just all in all. Now this has our dipole in our carbon-oxygen bond there. So that's less soluble because it's going to be a little bit more polar, but it's not as polar as this molecule here, which has very dramatic polar bonds happening there and there. So polarity is kind of increasing left to right there. Therefore, solubility in organic solvents, which again, to reiterate, is non-polar, is decreasing. So that's the general trend there. Now, if you can kind of get these concepts, that's a really, really good place to be because you can just springboard from that into kind of any, as long as you understand those concepts, you can kind of answer any question based on this topic. All right, so now what we're going to do here is predict the product formed when HCl is reacted with each of the following compounds. And we want to use Markovnikov's rule to predict the product as well. So a couple aspects here. Before we go through the answer. So yeah, this one here, we're only doing this compound. We don't have more than one compound, but I'm just going to take you guys through it and actually we'll have a look. So what we have here is, I'm going to draw it structurally because I just like to do that with my exam questions. So keep in mind, in order, especially this is multiple choice, you don't need to show any working, but do consider drawing out organic compounds in ways that make sense to you if it makes the question easier. Don't feel like you need to keep using the condensed formula or any other sort of like the line or structural formula. You know, whatever works for you, feel free to write it down on your paper and work through it like that. So here we have an alkene. So we've got, what do you call it? B3. We have propane here. Now, if we add HCl, so because this is an unsaturated compound, meaning that we have that double bond in there, it's going to undergo an addition reaction. Because unsaturated compounds, because of that double bond, we can break the double bond, turn into a single bond, and it gives us space on the molecule to be able to add in extra atoms. So if I just kind of redraw that a bit nicer, you can see here, if we break this double bond, make it just a single bond, and then we can add 2 more things here. So if we're adding HCl, that means we can add hydrogen. We can also add chlorine. Now that's what we would get as our product, except we haven't finished the question because we still need to use Markovnikov's rule. So Markovnikov's rule means that in these scenarios where we have a double bond, and see how we added the hydrogen and the chlorine, so these 2 things here. we can write them like that, or we can also put the chlorine here instead and the hydrogen here instead. So I want to figure out how do we actually figure out which one's which. So if we just pretend we have not placed these things yet, we have a look at the carbons that have these free spaces. So if you want to form the major product, so the product that forms most of the time. Now, the way it just works out with electronegativities, what I like to use, again, I have these little phrases, but they're really useful to remember, these kind of chemistry concepts, is the rich get richer. So what I mean by that is that the molecule that has the most hydrogens, most of the time is going to be the one to gain the hydrogen from whatever you're adding. So what that means is that if we look at, I'm just going to highlight them. So this carbon has 2 hydrogens on it, and this carbon only has 1. So when we add the HCl, one will preferentially go, so the hydrogen will preferentially go to the carbon with the most hydrogens. So that's our major product. And then in that same thing, so the chlorine will go to the middle one. However, our minor product is when the opposite happens. So that means this configuration here, where the Cl goes to the most hydrogens instead of the hydrogen, is our minor product. And then the hydrogen going to the one with the most hydrogens is our major product. So to predict the product here, I'm going to go with what happens the majority of the time. So if I'm just going to redraw it because that's gotten all messy now. That means we have, so carbon. Okay, can't see that, can you? Get a better color. So you have carbon, carbon, carbon. And like we said, major means the hydrogen will go here. And the chlorine goes in the middle there. So that means we have a chloropropane. So we can rule out the propene one there. And it's on the second carbon. So that means our correct answer is 2-chloropropane as the product being formed there. Okay, awesome. So a couple little concepts in there, which is definitely really good to just get some good practice of. Alrighty. Okay, cool. So what type of reaction is utilized to form disaccharides or polysaccharides? So let's have a look at the options we've been given. So protonation, glycosylation, addition, dehydration. So definitely what we don't have is addition. So really important. So when we're adding monosaccharides together to form either disaccharides or polysaccharides, we're undergoing a condensation reaction and we're forming glycosidic bonds. So we don't actually have a, oh, sorry, did I say we definitely don't have dehydration? Sorry, we don't have hydration. I was going to say because we're taking out water in a condensation reaction. Apologies, I think I got my words mixed up there. But condensation is removing water. So removing H2O. So that means we are essentially dehydrating the 2 monosaccharides. So we wouldn't call it glycosylation because we're not adding little like glycogen groups. I'm not even sure exactly how to describe it. And we don't have addition because that means we wouldn't be removing the H2O as part of that process, and we don't have protonation either. So we can call this dehydration. So what we definitely do not have is hydration. So the reverse reaction of breaking apart a disaccharide is a process of hydration, where we're going to be adding water back in to split it up into the monosaccharide. Okay, so now we want to identify which of the following compounds creates the following IR spectrum. So just a couple things to note as well for looking at your IR spectrum is that you don't look at anything below 1400. So I think on this curve, that's 1500 there. So anything below here, kind of anything that way, you disregard. So that means we're only looking at the left-hand side there. So what I would want to get up, I haven't got on me, but what we can do is actually, so the correct answer for this one is E. And the way we'd look at it is we consider the actual shapes. What peaks have we got formed here after that 1400 region, and correspond that to our the table in the data booklet where we actually have the values for the different wavelengths. So if you have a look at that, we can see that our, I can't remember exactly which one it is out of these ones up here, but we have a triple bond present, and this is the only molecule with a triple bond, and it corresponds to that kind of dip in the wavelength there. And then we have the same type of question here where we want to identify compound from the IR spectrum, again, disregarding everything below here. I think we call that the fingerprint region, but yeah, we don't ever look below 1400 in terms of a wave number. So if you want to consider what we're actually creating, we have A. So we have an OH group present from the actual peaks that we've got here. So again, have a look at the table in your data booklet. You can download the slides again and kind of go over that again with the actual data next to it. But the correct answer there for that question is A. And that's the main kind of process with interpreting IR spectrum as well. So then we have the same question, again, just in interest of time. You can access these slides, download these and have a look at them. So that's kind of just working down through all of the molecules there. So if you want some more practice questions, those are available in the slideshow itself. Okay, cool. So the next one we have here is, for the mass spectrum of 3-pentanone, explain the 3 main peaks. So we have what we call our molecular ion peak being our highest peak there. Then our most abundant one we call our base peak. And then we have other fragments present down here. So the IR spectrum gives us information on what functional groups are present, so it can help us identify what class of molecule we're dealing with, whereas our mass spectrum, what that is predominantly dealing with is looking at our actual different fragments, so telling us the actual size of the molecule that we have. So if we have a look at what these all correspond to, so they're different kind of fragments of this main molecule. So if we have 3-pentanone, that's what's going to make up our molecular ion. So our most abundant mass charge ratio, so the 86, that's the mass of the biggest fragment that we can get, except the fragment is just the whole molecule itself. So that's what we have for our molecular ion there. Now for the base peak, that's when we've sliced up. So the process of mass spectrum is that we take these molecules, bombard them with energy, and we basically just split it up into lots of different pieces. So if we split up the molecule there, what's on the left forms our base peak, so the most abundant peak. And we're always going to be splitting, by the way, along the parent chain. We never split off like some weird angles. We always just kind of split off pieces of the main chain like that. But yes, our base peak is the fragment produced on the left, so that has a mass of 57, which is why it's valued at mass to charge ratio of 57. Then this here is what's forming our peak at 29. So I'll just kind of indicate that that's what those two are. So that's our most popular fragments, if you will. So when you bombard lots of 3-pentanone with energy, you end up with all of these fragments being the most commonly created ones. Alrighty. Now we're going to have a bit of a practice of a longer, chemical synthesis question. I think that was our, yeah, so now we're going to start our chemical synthesis topic. This is a longer question, and it's basically entirely on the contact process, so everything about it. So what is the contact process? What are the conditions used for the process in the industry, and why are these conditions used? Include your pressure, temperature, and any catalysts used. So have a think about that one, and we'll go through, I'll speak through a bit about short answer questions in a second. So I'm going to have some water. So what I would probably do for this short answer question is actually just starting with breaking down the question itself. So we want to answer what is the contact process. That's pretty much going to be looking at what is it producing. So what are the conditions used for the process in the industry? And why are they used? So we actually need to probably relate it to So if we have a certain condition, we need to actually relate it to the equation of that step or process. And then specifically, we want to think about pressure. So I'll just highlight this. We want to think about pressure, temperature, and any catalysts used. So I was going to say for this, so we have the contact process. I know we have biodiesel production, the Haber process, all of these kind of different, unique topics, subtopics, I guess. A good way to study them or to revise them is to create a really, really succinct summary for yourself, whether it be in your notes, I don't know, flashcard or whatever you find useful. And then, once you've got that, actually using that as a kind of springboard to make a longer answer. So as long as you have your main equations, what is it producing, the temperature, conditions, pressure, all those kinds of things, down kind of in a really just short format, that's going to form the basis of your mark allocation in the marking guides for these questions. They really want to see that you hit each individual part correctly. Because if you write a massive, massive paragraph, doesn't matter if you write 1,000 words on the contact process, but if you don't actually mention exactly what the marking criteria wants you to address, then you're not going to be assigned any marks. So hopefully you've had a chance, or if you haven't, this kind of holiday time leading up to externals is a good time to start looking at the practice papers and the marking guides. So once you do a practice paper, have a look at the marking guide and make sure you pay attention to how they actually allocate each individual mark. But going back to this question, so this is very, very long, so please don't think you have to write an essay for this type of question realistically in the external. I've just kind of put all the information here that we could possibly include. So going through it, so the contact process is creating sulfuric acid from sulfur and oxygen. So the first part is when you burn sulfur with excess of dry air to allow more oxygen for the next part of the reaction. So we're making SO2. And then the sulfur dioxide is reacted with oxygen in the presence of a vanadium oxide catalyst. That's the equation there. And we get sulfur trioxide as a product. And then we take the sulfur trioxide and we dissolve it in concentrated sulfuric acid to produce oleum. Then we take the oleum and we react it with water to produce more sulfuric acid. So it's a bit ironic because we use sulfuric acid to produce sulfuric acid here. No, not here. Here and then here. But that's just part of the process. You end up getting more sulfuric acid out of it in the end. So overall, we have a 1-to-1 ratio of oxygen, and this maximizes the efficiency of the reaction in terms of equilibrium, mixture, and rate. But the two main dot points in terms of conditions that I'd focus on would be these two here. So the second reaction is exothermic. So a lower temperature will result in a higher conversion of reactants to products, except the lower temperature will also reduce the rate of reaction. So what this means is that we use a temperature of about 400 to 450 degrees to produce a fairly high proportion of sulfur trioxide, but in as short as possible a time. So that's the issue with temperatures. If you lower the temperature too much, you're not going to have a high enough rate of reaction. But if you lower it again, but if you make it too high, then you're not going to be favoring the fact that it's exothermic. Okay, so then the pressure used in the reaction is close to atmospheric pressures. So then in the reaction to create sulfur trioxide, a higher pressure will favor the creation of that product. However, even at atmospheric pressures, there's a 99.5% conversion rate of reactants to products. Producing higher temperatures is expensive, so then atmospheric pressure is chosen just to minimize the cost. So you can see that these processes don't purely just operate on like the raw chemistry and what makes it more efficient. You also have to consider real-world applications like cost and materials required to maintain certain conditions. So again, you can have a copy of these slides and watch this recording back if there's any notes you want to take from there to add to your own. But that's kind of the main processes. Making sure we mention, equations, pressure, temperature, catalysts. What is it actually making? All right, so then the next question we have is to compare the two methods of ethanol production with regards to the reactions and conditions in each. So first thing you have to do is actually remember what are the two ways of producing ethanol, and then we need to compare them. So like I mentioned right at the start of today, another good thing to get in the habit of doing with your short answer questions is actually breaking down the cognitive verb there. So what you might notice with questions, for example, that use compare, is that there will be different questions that use contrast. So if you actually go onto the QCEE syllabus and you look at the, like for chemistry, go to the chemistry syllabus and you look at the definitions right at the bottom of the glossary, you'll find definitions on compare and contrast. So compare is where I believe we are looking at similarities and differences and also the significance of each. And then contrast is when we're pointing out the differences between two things. I'll actually have a look now at what exactly it is. Let's double check on our... Yes, so contrasting is where we're looking at the specifically outlining the differences. Comparing is looking at similarities and differences. So we'll go straight onto the answer and have a look at this. So we have two main processes. So the first one is our fermentation. The second one is our hydration of ethene. So fermentation is where we have, it's basically a batch process. What you do is you take your organic matter, leave it in a container until fermentation is complete. It's fairly inefficient though. Then hydration of ethene is where we take ethene, we hydrate it with water, and then that turns it into our ethanol. So it's a little bit more efficient, but if we want to compare it on a few different kind of metrics, we have rate of reaction, reaction conditions, use of resources. So considering rate of reaction, fermentation is very slow. Hydration of ethene is a lot faster. So for reaction conditions, so fermentation uses gentle temperatures and atmospheric pressure. Hydration of ethene uses high temperature and pressure and needs lots of energy input. And then for the use of resources, fermentation uses renewable resources based on plant material. The issue with hydration of ethene, even though it's a lot more efficient, is that it uses finite resources based on crude oil. And then for the similarity is that they both, I guess, produce ethanol. That's the main similarity between the two. Yeah, so that's a kind of good way to structure an answer, is to pick different metrics of comparing things and then commenting on each of the two methods or whatever you're comparing, comment on each one, and then move on to your next metric. Kind of gives your answer a nice structure there. All right, next one here for chemical synthesis. So we want to calculate the yield of a reaction that theoretically could produce 25 grams of carbon dioxide, but only resulted in 20 grams of carbon dioxide when measured. So this is just a reminder that you can definitely be asked to use the other formulas that aren't specifically linked to a syllabus objective in Unit 3, Unit 4. So if you remember back in your data booklet, you have, for example, your, like percentage yield, those kinds of equations near the start of the data booklet. They can definitely still be assessed and used in your externals. So what we might do is actually just go forward and have a look at this next part here. So if you want to calculate the yield of reaction, so if we want to theoretically produce 25 grams of carbon dioxide, but we only actually got 20 grams. So the equation is that yield percent-wise. So we have actual yield over theoretical yield, and then we multiply it by 100. So we have actual, or we can call this our experimental, is another way we can kind of phrase it. Over our theoretical. And then we're going to multiply it by 100 to give us our value in a percent. So if we have that there, we have 20. That's what we actually got. Theoretically should have produced 25. And we multiply by 100. And then, what do you call it? We pop that into our calculator. Multiply by 100, and that gives us our 80%. So correct option there is D. So again, if you're really confident, because this is a multiple choice question and you wouldn't have to show working for this, you could just calculate it, just put it straight into a calculator and then answer the question like that. But that's just an example of another, especially with more for chemical synthesis, this kind of question might pop up. You might also find in your practice exam questions that questions tend to have sometimes a lot of marks assigned to it, but it's broken up into lots of little steps. So this could be an example of maybe 1 mark in a like 7, 8, 9, 10 mark question. Alrighty. Now that is actually the end of the practice questions that we had set for today. So the last little bit of today, we'll kind of just spend, I think the session will only have about 15 minutes or so from here. So that will just be time for you guys to please ask questions now about anything that we've gone through. The other thing I'd like to mention actually is the fact that you can watch this recording back after the session is over. You can share it with your friends, anyone else that wants to kind of have a look at it. I definitely recommend you do that as part of your revision for external exams. And at this point of year 12, I think a good thing to be focusing on is now starting to clean up little gaps in your knowledge. Use the syllabus as a kind of place to keep yourself accountable to the syllabus, so you can go through and then identify or highlight the dot points that you're struggling with. And then after that, then going and doing practice exam questions and working your way up to doing a whole set of questions in exam style. So what I mean by that is picking questions from lots of different topics, giving yourself a time limit, and obviously not referring to any notes or anything else while you're doing the questions, and always make sure to mark your answers as well. I cannot emphasize that enough. There's really no point in doing a practice question unless you mark it and figure out if you've got the right answer. So if you've got any questions about how to tackle any of the topics we've looked at, if you have any concerns here about how to revise, again, please ask in the Q&A. You can spam it with as many questions as you want. Otherwise, yeah, thank you guys very much for coming along today and taking part in our lecture series. We have a lot of lectures happening this week on a lot of different subjects, and even if one's already happened by now, you can still go back and watch it later. So please go and sign up for any other lectures that you haven't registered for yet. Otherwise, apart from that, I wish you guys all the best with your external exams. I really hope everything goes well, goes smoothly, and you do still have quite a decent amount of time. So if you're in panic mode, take a breath, they'll be okay. You've still got a lot more time than maybe you feel. But yeah, again, you can download the slides as well, go through the answers to the questions that I've put in the actual slides that have been put in the slides themselves. And yes, again, look forward to seeing you hopefully in another lecture. All the best for the rest of the year. Any questions about even uni degrees, anything, we've got the next few minutes to go through any of that. So yeah, thanks guys for tuning in.